All right, so we're here to talk about a little bit of error analysis. So we can kind of go along with that previous video where we talked about dealing with some of the errors in your measurements, but this is a little more detailed look into error analysis. Okay, so first thing we need to talk about is our two types of error that can occur when you're doing an experiment, and that is systematic errors and random errors. So systematic errors, these are the kind of errors that are occurring because of something that is being done in the experiment. And if you do the experiment the same way repeatedly without changing anything, you'll get the same exact error each time. The simplest example I can think of for this is if you just have your ruler not lined up with the edge of an object and you are measuring it, then you're going to be off when you try to tell what the length is if you don't have it lined up with the zero part. So if you do that same thing and have your ruler lined up the same way every time, you're going to be off by the same amount every time. So this kind of error stays the same. Between measurements. Too many E's there maybe? I don't know. Measurements. I'm not sure about that E. But anyway, and then the other one is the random error. And this random error is due to things that are beyond the control of the experiment, at least the person doing the experimentation. And every time you do a measurement, it's going to be a little bit different of a random error. So this one will change between essentially identical measurements. And one of the big ones where I saw some of the most random errors ever in any of my experiments was doing radioactive decay, where you would read it and they were just, read radioactive decay from a sample, and over the amount of time that occurred, and there would be just wild differences in the number of decays that occurred over the few seconds that we would watch it in the little counter. So you have to be careful about this. Some is random, you can't really do anything about it. It might have to do with the wind blowing or something like that. It might be with you doing you're trying to time something, and your reaction time isn't exact and it changes each time you do it a little bit. Versus systematic, where you're just getting the same mistakes over and over again. Systematic errors, they're kind of hard to deal with because you don't necessarily notice that they are there. So you got to be really careful if you're getting a consistently wrong thing. But good news, usually that means is you can make an adjustment to one of your instruments or how you're using it and fix the entire experiment. So you have to be careful about that. I also wanted to add on to the error size from measurements that we talked about before, was that I didn't really talk about measurements where you had this kind of random error, like measurements where you're making it by hand with like a stopwatch or something, because you might look at the stopwatch and it tells you how accurate it is down to the centiseconds. For example, you could have something like, oh, it was 35.23 seconds, and you look at that and you say, from my rules that I talked about before, that this 0.3, that you would do plus or minus 0.01 as your uncertainty. But most likely your reaction time is not accurate down to 100th of a second like that. And so you would have to do a whole bunch of measurements repeated over and just look at what variations you have in measurements over the same trial, the same exact experiment being done, to kind of see how good and how accurate of a measurement you are making. So you would definitely not want to make this 0.01. I've had a lot of students do that before. They make this 0.01 as their uncertainty in their timing, and then their answers are off. And they look at it and they finally propagate their error all the way through, and they get an answer and they say, oh, it's not within experimental uncertainty, and they think they're wrong. Where if they had been a little more generous in their uncertainty on this, it would have actually put their answer within uncertainty of the value they were looking for, and they actually did do a good experiment except for that. So you really have to look at how consistently you time, and it's a little different for each and every person and how good of a timer you really are. So just a little aside there on that. When you're timing something by hand and relying on your reaction time, You got to kind of take that into account. So now let's talk about how do we combine these errors. We've done these measurements errors, we've got all these errors, but then a lot of times in physics you have to combine numbers together. You have to multiply things together and divide them together and add them together. What do you do with the error when that happens? And we have about 3 little rules here. Really, it's just 2 rules. The third one is basically just an extension of the second one, but it's not so bad. So how do we combine or propagate errors? How do we combine errors when we do all of our math and combine our numbers together? So for this one, the first is addition and subtraction, and this is pretty simple because all you really have to do here is add the uncertainties together. So if you looked at something and I told you it was like 2.5 plus or minus 0.1, and then you had to add on to that, let's say plus 10.0 plus or minus 0.2, what are you going to do with this? Well, if you look at this, there's a big range that this could fit in, and this could be as big as 2.6 over here, because it's plus or minus that 0.1, plus 10.2. So on the high end, we might get 12.8. On the low end, this could be 2.4, and then this one could be 9.8. And so when we add those together, we would get 12.2. So if you look at this, we have a range of 0.6 here, and it would be half of that range. It would be our 0.3. Because when we actually do add this 2.5 plus this 10, right, when we do it the normal way, we would get 12.5, which is going to be right in between. It's 3 above the 12.2 and 3 below there. So it would be plus or minus 0.3. That's the range we could get for this. Well, if you notice, 0.2 plus 0.1 is just our 0.3 over here. So the simple thing to do here when you're doing addition and subtraction is just to add up the uncertainties. It works the same for subtraction, changes to a subtraction, redo this, and you'll get the same sort of variation in it. You just add the absolute uncertainties there. Now for multiplication, for multiplying and dividing, it's a little different because you could maybe try to want to go through and do the maximum min thing and want to go through and do this same sort of thing again. But it turns out that it's pretty simple. If you just take the percent uncertainties, instead of adding just these absolute uncertainties, you can just add the percent uncertainties. Add the percent uncertainties. So for example, if we had 50 plus or minus 5 meters, and we traveled that distance in 10.0 plus or minus 2 seconds, we'd get a big variation. We could do the 55 and the 10.2 and or divided by the 9.8 and come up with a high end number, and then we could do the lower end number or things like that. But there's no need to do this, and we're definitely we can't just add 2 seconds and 5 meters because that's against the rule. They don't have that. But if we change these to percent uncertainties, we can add percentages together. So if we look at this, this is 5 out of 50, 5 out of 50, which gives us a 10% uncertainty in that measurement. In this one, we have a 2 out of 10, which is a 20% uncertainty. And so we can combine these. We do 50 divided by 10. That gives us 5 as our answer, and then plus or minus, and it's just the addition of these two percents. It's plus or minus 30%. And so whatever 30% is of 5, you would just find that, and it would be plus or minus that. You can leave it as a percent uncertainty. That's fine. You don't need to actually convert it back to the old absolute uncertainty, but you're welcome to just take 30% of your final answer, and that's how uncertain your answer is going to be. So just be careful with that, and that's true for both multiplying and dividing. Now, what about when you have something raised to a power? Because that happens often in physics. You'll have 1/2 a t squared or something like that. We have it raised to a power. Well, if you think about it, stuff raised to a power is really just the same as multiplying a bunch of times. If I have, y equals a to the nth power, this is just a times a times a times a, n number of times. And so all I would really be doing is doing this same rule up here for multiplication n number of times. And so if I want to just add something n number of times, well, multiplication is repeated addition. And so your uncertainty would just be n times your uncertainty. Whatever your power happens to be, it would be n times that percent uncertainty here again as well. So n times that percent uncertainty. And you also can do this for fraction powers. So if it's to the 1/2 power, this would be 1/2 times your uncertainty. All right. If this was to the 3rd power, it'd be 3 times the percent uncertainty in that number. So that pretty much covers how you actually carry your propagation of your errors through. Now, be careful because some of these you might have to do things where you're adding and subtracting and multiplying and putting things to power. So you have to do it one step at a time. Do your first calculation, find the percent error, then do the second one, follow the rule for that second one, and just propagate it on through. Take your time, follow these rules, and you'll be okay by the end. All right? Now, what do we do with graphing these errors? How do we go along graphing? How do we propagate our errors into graphs? Because what will happen is we're going to have to do some graphs at some point. Make sure this line is big enough. And you're going to put these points on your graph. And you're going to say, all right, here's a point here and here and here and here. And then we're going to have to do lines of best fit for this. We're going to have to try and find, is this a linear relationship? Is it exponential or whatever it is? We have to do lines of best fit. Most of the time we're going to try and linearize things so that it is a straight line. But then how do we include the error on this? Well, we do this with error bars. You would go in and say, all right, however big the error is on this axis, you would say, say it was plus or minus 1 centimeter, then you would have to bake an error bar line above this one equivalent to 1 centimeter and below it, so it'd be plus or minus a centimeter. And you would have to put this on all of them where that was the uncertainty. And so you would have something like this on all of them. Error bars for the vertical errors. And you could also have uncertainty horizontally. Say this was your time and you were off by a second. So you'd had error bars across here for these measurements. And you have to put these on here. And these aren't here just for looks. You don't put them there just so people can say, oh yeah, there were uncertainty. There was uncertainties in those measurements. They actually have some meaning. So when it comes time for me to do a line of best fit, say I'm lining this up, I'm not doing it with Excel or anything, and then I have to try and get something in there. Well, basically my line has to match the uncertainty of all of these. And so if I were to take and draw a little square around each part that matched up with those uncertainties, my line is going to have to pass inside the square on each of those. Because if it doesn't go with inside this square, then that point actually doesn't agree with what line you drew. Because if my line comes up here and is above it and doesn't go through that square, then that point doesn't actually have the chance of being on that line. It would be impossible for it to because it's outside the possibility of that point. And so you have to make sure that that's going to line up with what is in there. If you have a point that does not, absolutely no matter what you do, you have a measurement and a point that should be in the straight line, but it is not, then you may have an outlier. You may have had a mistake in that measurement. And of course, you'd want to go back and verify and check. Now, it may turn out that something was linear and you discovered some new physics where there was like a dip or something in there, which could have happened. Maybe you did discover some new fundamental physics thing, but most likely you made some sort of mistake at this level, and you'll want to go back and retake that measurement and make sure that it can actually fit in the line that you are expecting. So when you come in, and I don't know how great of a line I can draw here, but you're going to want to kind of just eyeball this line through, and it's got to hit through everything. And so you do a line like that. You can say, all right, that's my line of best fit. I can take my slope from it. I can find my areas under it, whatever I need to do. But then how do you get error from this? Because if we're taking a slope, which we'll do often, we'll take a slope to get a measurement. We'll find a slope to find the acceleration due to gravity, the slope to find something with it. How do you get error from this line? Right? This is a line of best fit. It seems like there's only it. Well, what you have to do is basically go in with your little squares and your uncertainties, and you have to try and draw in a line with the greatest slope that'll actually fit and the shallowest slope that'll actually fit. And then you look at the uncertainty in those other slopes and see what your uncertainty is. So if I tried to come in here, and again, I may not have done these just so perfect, but what is the steepest line that I can fit in here? And maybe I can do something that's kind of like that. And maybe I'd mess that up, but I nick that corner, let's say, a little bit. And now that's a steeper line, and maybe that's the steepest one I could do. I'd want to line a ruler up on there and try and move it around until I found the steepest line I could. And this would be my maximum slope. This would be my high end. It would be plus this. And then I could come along and do another one where I tried to come in here and do like the shallowest slope that I could, and maybe I could kind of fit something like that in there. And then that would be that. And so the red line would be my actual measurement, and the two green lines would be my plus or minus. And I'd look how far off they are and see what they give me for plus or minus on the slopes of that. But you have to be sure that your actual best fit lines, they are going inside here, because it's not possible, assuming you made your measurements correctly and you did your uncertainties correctly, it should not be possible for the line, which is supposed to be all of the possible measurements you could have made. You're interpolating between these points and finding all the possible measurements that could have been made. It wouldn't be possible for something to not be on that line. So be very careful that your lines of best fits and your maximum lines, they actually fit through your uncertainty squares. They have to go inside the uncertainty on each of them. I couldn't come along here. Let's say I did this in I couldn't come along here and say, all right, here's my line of best fit, and do like this, and just totally skip this point and even skip that point. That line, that would not go over well. Okay, that would be an incorrect line. You maybe get lucky that you get the same slope because maybe you just shifted the line down and it did match that original slope, but it wouldn't get you points on a test, and it wouldn't get you points on like the IB exam. All right, I think that is all.